All right, everyone, Mr. Graham here for kinematic equation number 3, where it comes from. I'm not going to use the graph for this one. I'm actually just going to use the first two kinematic equations in order to algebraically determine the third. Understand that the reason we have multiple kinematic equations, there's the bell, is because some problems we have certain unknowns, other problems we have other unknowns, and so you got to look for which quantities you actually know in order to solve for the relevant unknown. Very often you don't know how much time went by. You don't know the time interval over which the motion happened, and so we're going to eliminate the parameter t from these two equations by substitution, by direct substitution. So I'm actually going to start with kinematic equation number 2 here, delta x, and I've written it in delta x form just to make the algebra a little less cumbersome. Delta x is going to be the initial velocity times time plus 1/2 times the acceleration times the time squared. Again, very often we don't know what the time is. We don't know over what time the motion happened, and so I actually want to eliminate that parameter. And I'm going to do so by taking kinematic equation number 1. I'm going to take kinematic equation number 1, which says final velocity equals initial velocity plus the acceleration times time. I'm going to solve this for the time t. I'm going to subtract delta x from both sides. I'm going to subtract the initial velocity from both sides. And then I'm going to write v minus v naught, or final minus initial velocity, as delta v is going to equal the acceleration times time. And again, I'm trying to eliminate the parameter t, so I want to solve this equation for t. So I'm going to divide both sides by the acceleration a. Now t is by itself, and I know that the time t is just going to be the change in velocity divided by the acceleration. So I'm going to use this. I'm actually going to substitute that delta v over a in for the t's in kinematic equation number 2, and then just simplify using my algebra. So when I do that, I get that the displacement delta x will be equal to the initial velocity times delta v over a. Delta v over a plus 1/2 times the acceleration times the time squared now. So that's going to be delta v over a, that whole quantity squared. Now I just need to do some algebra. Yes, it's going to be a little tedious, but at this point you need to have the algebra skill in AP Physics C. You'll have a real tough time if you don't have algebra skill. It's really on point. Because we are going to be actually throwing calculus at this stuff starting very, very, very soon. Okay? All right, so I'm going to go ahead and start simplifying here, and I'm actually going to expand out my delta v's. So I will have v naught, which is in the numerator, times delta v, which is going to be final minus initial velocity, and all that gets divided by the acceleration a, plus 1/2 times the acceleration times, now this, you should know that that power applies to both the numerator and the denominator. So I'm going to have to multiply, or I'm going to have to square the quantity v minus v naught and square the acceleration in the denominator. And you should notice that the numerator acceleration cancels with one of the denominator accelerations. And then I'm going to go ahead and distribute the v naught over both of the terms inside the parentheses here. And then I'm going to foil. I'm going to foil here in order to simplify the right side. So I'll have delta x equals, I have v naught times v minus v naught squared whenever I distribute over the acceleration, plus numerator here, when I FOIL that, I have v squared minus 2 v naught v plus v naught squared all over, the 2 is still there in the denominator and the a is still there in the denominator. Now note that these are not common denominators, but I can make it a common denominator by just multiplying the left side here, numerator and denominator, by 2. Then I'll have a common denominator of 2a. So when I do that, I get delta x equals, I distribute all this over, I get 2 v naught v minus 2 v naught squared, plus what I have over here, v squared minus 2 v naught v plus v naught squared, and all of that is going to be over 2a. Then I noticed that I can combine some like terms. I have a 2v naught v and a minus 2v naught v, so those cancel out. Please get in the habit, if you're not already there, of crossing things out as you get rid of them. There goes the bell again. It's just a good habit to get into. It keeps you from bringing things down and making mistakes in the next step. All right, so I'm going to have delta x equals, what am I left with? Negative 2v naught squared plus, oh, I'm sorry, I have more like terms. I have negative 2v naught squared and a positive v naught squared. So whenever I simplify those, negative 2v naught squared plus v naught squared, I'm going to have a negative v naught squared. What else do I have left in the numerator? Plus v squared. All that divided by 2a. And then I can multiply here both sides by 2a because we don't like fractions. I don't like fractions. If I can get rid of them, I definitely do. So on the right side, the 2a's will cancel. Numerator 2a, denominator 2a. And so I have 2a. And here delta x I can write, just to make it look like what you see on your formula sheet, I can write that as final position minus initial position. That's going to equal what I have on the right side. I'm going to reorder. I'm going to put my positive v squared in front of my negative v naught squared. And then to this, I can just add v naught squared to, oh, no. Yes, I'm going to add, v naught squared to both sides. So it goes away over here. And notice I now pretty much have the third kinematic equation. On one side, I'll write it, running out of room. On one side, I have just the final velocity squared. On the other side, I have the initial velocity squared plus 2 times the acceleration times the displacement x minus x naught. And sure enough, that is kinematic equation number 3. We've eliminated the time from the equation. Therefore, if I have a problem that involves kinematics that doesn't give us how much time is elapsed over the motion, then the third kinematic equation is what we use. All right, there you go. There's the kinematic equation.